All right, welcome to the online Causal Inference seminar. Today we're excited to have Jann Spiess, who will talk about improving inference from simple instruments through compliance estimation. Jann Spiess will stop from time to time and take your questions. Also in Q&A, there's one of his collaborators, Stephen. So yeah, please submit your questions there. After Jann's talk, we'll have a discussion by Damian and Kozbur. Questions today will be handled by Emma, so I'm going to switch over to her now.
All right, hi everyone. So as always, we are handling questions through Q&A. So please use the Q&A to submit your questions, not the chat box. And as Dominic said, Stephen will be answering questions there. Some of your questions may be asked live. And yeah, just keep that in mind. We'll try to get to all of your questions. Yeah, so keep them coming. All right, then we'll switch over to Jann, who is welcome to start this talk.
Thank you so much, and thanks for having me. Very excited to present here today on improving inference from simple instruments to compliance estimation. I'm in the OIT group at Stanford GSB, and I'm joined today by my co-author, Stephen, who is at Columbia Public Health. So what I want to discuss today is inference on causal effects. And I'm going to assume that there is some treatment D and some outcome Y. We want to estimate the effect of D on Y. However, I'm assuming that there is some confounding going on, meaning there are some unobserved confounders that drive both selection into treatment and the outcome itself. And the way we want to overcome that in the talk today is the standard instrumental variables approach of assuming there is some instrument that affects the outcome only through the treatment, but is not also affected by the unobserved confounder. So let me give you a very concrete example. So assume we have some medication and we want to estimate the effect of that medication on health outcomes, but then there may be a problem with selection where we may assume that people with bad health conditions are both more likely to take the medication, but also have worse health outcomes. So if we were to naively estimate the effect of medication on health outcomes, we may come up with the wrong causal effect. So now assume, however, that we have some instrument available. So some encouragement, some nudge that makes it more likely that people take their medication, and that we actually randomize that encouragement so that it is uncorrelated to the underlying health condition. So in that case, we can still back out the effect of medication and health outcome among those people who react to the encouragement. And so in this general framework, one standard way of doing is to use a two-stage least square estimator, which we can conceptualize as a prediction problem, where we first predict treatment D from the instrument Z. So effectively, we project the treatment onto the instrument. And then rather than estimating the effect of the outcome and of the treatment D on the outcome Y, instead, we now estimate the effect of the predicted treatment, so of the projected treatment onto Y. And this gets around the heterogeneity because now we're only capturing variation in the treatment that is imposed by the instrument and allows us to estimate the causal effect. And so therefore, there is a tight link here between IV estimation of causal effects and a prediction problem, and then specifically the prediction problem of predicting the value of the endogenous treatment from the instrument. And this parallel between instrumental variables and prediction problems has sparked an interest in using machine learning to improve the strength of instrumental variable approaches, and specifically, for example, to use Lasso in the first stage, or to use rich regression, or to use more generic machine learning regressors in order to construct instruments from many complex, in order to construct better low-dimensional instruments by predicting them from a high-dimensional set of instruments. And the typical setting there is basically we have a high-dimensional set of instruments, and from this high-dimensional set of instruments, we are predicting the treatment, and we can use techniques for machine learning in order to improve that first-stage prediction problem, which then in turn improves our ability to make inference on treatment effects. So the setting I want to look at today is going to be slightly different. Specifically, I'm going to consider a case where the instrument itself is actually simple. So for example, take the case of a medical RCT like before, where maybe the instrument is some binary encouragement to take up treatment. And in that case, some of those machine learning methods may not be directly applicable because I don't face a high-dimensional prediction problem in the first stage. However, I may also have some additional covariates X available. And here I'm assuming that those covariates, those baseline features, are not actually correlated with the treatment in any way. So the treatment is randomized independent from them. And the question today is then going to be, how can we leverage those simple instruments with potentially high-dimensional pre-assignment covariates to improve IV inference? And just to be clear, in principle, all the existing results on using machine learning in the first stage still remain applicable, because effectively we can think of this as having a high-dimensional instrument space where we include interactions between the instruments and the features. But exactly the structure, the nature of how these instruments look like that combine a simple instrument with potentially high-dimensional controls that I want to talk about today in the talk. So specifically, I want to focus on a very simple case where the instrument is binary and the treatment is binary. And I want to highlight the main way in which we will leverage these additional covariates. And to do that, I'm coming at it from a completely opposite direction. I'm coming at it from the simplest possible IV setup, where I'm assuming that both of those, both instrument and treatment is binary, and I can therefore classify the people in my sample into 4 categories. So specifically, using the standard local average treatment effect framework, I now classify people into compliers, which are those people who actually react to the treatment. So those are people who take up the treatment if they are assigned to the encouragement group and don't take up treatment otherwise. And they're always takers, which always take the treatment, no matter whether they are assigned or not. They're never takers, who never take the treatment, whether they are assigned or not. And finally, there could in principle also be defiers, like people who take up the treatment if they are assigned to the control group and do not take up the treatment if they're assigned to the encouragement group. And I will assume today, for most of my talk, that these don't exist and rule them out, so that basically everybody is only reacting in a positive way. So if we have those remaining 3 types of compliers, always takers, never takers, here is a simple observation, which is that our ability to estimate causal effects relies on the presence of compliers, because those are the people who actually react to treatment as we change the value of the instrument, while the always takers and the never takers don't actually contribute any effect and instead only add noise to our observations. And so to drive that point home, let's think of a hypothetical case where I have 1,000 compliers, so 1,000 units in my sample, which actually react to the instrument, so that if I set the instrument to 1, their treatment will also be 1. If I set the instrument to 0, their treatment will remain 0. And I consider 2 cases. In study A, they are only compliers. So those 1,000 compliers make up the full sample. In this case, I don't actually have an heterogeneity problem, and I could simply estimate the effect of the treatment on the outcome by comparing people assigned to treatment versus those not assigned to treatment. Then I have a second study where I instead assume that they're also always takers and never takers. And those 1,000 compliers are among a total of 4,000 observations, so that the compliance rate, the probability of actually responding to the treatment, is only 25, of responding to the instrument is only 25%. And I now want to ask how the variance differs between those 2 cases, which is based on the same number of people who react to treatment. And so the answer is, if you do some standard approximations here, and you're assuming that the error terms are all homoscedastic, so that every unit contributes the same amount of noise to our estimation, then the variance is proportional to 1 over the sample size times compliance squared, or if we want to hold the numbers of compliers fixed, the variance is effectively linear in the total sample size. So that means that in this case, if we had some ability to actually find who the compliers are, in study B, we could actually cut our variance by a factor of 4. So specifically assume we had some covariates available, and using those covariates, we would be able to find who the compliers are. Well, then identifying them perfectly would reduce the variance to 25% of the standard 2-stage least squares estimator that we would use on the sample of 4,000 observations here. Okay, so my argument in the talk today is that this way of using covariates is one of the right ways of thinking about using covariates for improving the strength of IV regression. And that in practice, we can implement that using tools for machine learning. So for that, let me now move over to a small simulation example, where on the left, you see the people assigned to the control group. So those are the ones where the instrument value is 0. On the right, those assigned to the treatment group. So those are the ones who are encouraged to take up treatment where the instrument value is 1. And so what we see here is that there are red dots who actually end up not taking up treatment and blue triangles that end up taking up the treatment. And we see that the concentration or the fraction of those who took up treatment is higher on the right than on the left. And so that means here our instrument had an effect on take up, and we can use that in order to back out treatment effects. But that can be very noisy because overall we basically have to back out the effect from an average of the right versus an average on the left. Now assume instead we have some additional covariate available, according to which we can predict outcomes, but we can also predict likely take up. And let's assume on the x-axis we have some patient characteristic in this example. And we see that the probability of taking up treatment actually changes with that patient characteristic. So in this case, for example, it would be the case that the people on the left will never take up treatment, no matter whether they are assigned to the instrument condition or not. So those would be the never takers, while the people on the right will likely take up treatment no matter whether they are assigned to treatment or not. So on the left, we have the never takers, on the right, we have the always takers. So both of those will only contribute noise. However, it's in the middle where we have the compliers, which are those people that are likely to respond to treatment because their probability of taking up treatment is higher on the right than on the left. But we can use the characteristic in order to identify that group where there is indeed a response and we can identify the treatment effects from. And so the idea today is to exactly use that and not just do selection, but actually weight by the probability of taking up treatment in order to improve the precision of our IV estimates. And so here is the program for today. So first of all, I want to start from how can we actually use covariates and then come to a characterization of valid instruments that use covariate interactions. I then want to relate the resulting instruments to efficient weighting by compliance in a potential outcomes framework, propose an implementation using sample splitting and heterogeneous treatment effect estimation tools for machine learning, for which I will provide asymptotic theory and tools for valid inference. Then, if I have the time, document the performance of that in a simulation study and discuss some extensions. Now, before we go there, I want to be very transparent that we are by far not the first to propose weighting by compliance, and that even the implementation we propose is very similar to one that has recently been proposed by Huntington-Klein. And so, therefore, let me go in some detail over the existing literature that we are aware of in this area. So first of all, the idea of weighting IV by compliance, the earliest reference that explicitly deals with that we were able to find is from the biostatistics literature by Joffe and Brensinger in 2003. There's also some recent work in econometrics playing off the similar ideas. So specifically, Abadie and co-authors have a paper of selecting subgroups by compliance and then weighting by compliance among the selected subgroups in order to avoid bias from weak instruments. Nick Huntington-Klein has probably the most related paper where he also uses tools for machine learning in order to weight by compliance and targets the small sample bias by doing so. And then finally, there's a very small number of empirical work. I've noted one here by Leon Einarf and co-authors that actually uses similar techniques in empirical applications. So specifically, Leon and co-authors have a paper where they select a subgroup by compliance and then run their IV analysis on that subgroup. There's also recent interest in the use of covariates in IV in order to ensure that IV is valid in the first place. So Kirill Borusyak and Peter Hull have a recent paper on showing how to recenter instruments to ensure that they are valid if exposure to the instrument is itself exogenous. And they also talk in a very similar way that we derive here about weighting for efficiency. And then finally, Jann and co-authors have a recent paper on using generic machine learning predictors in the first stage of IV that also explicitly considers the use of covariates, although in the harder case where these covariates are not necessarily independent from the instrument. Another very related line of work is by Edward Kennedy and co-authors on using compliance classification. So our ability to be able to find who a complier is, who compliers are, to basically characterize the sharpness of an instrument in order to add one additional diagnostic tool and the ability to extrapolate better to the IV toolkit. And then finally, maybe the most direct precedent to our work here is a chapter in Stephen's dissertation where he was talking about using compliance for experimental design. So for example, only including compliers in your experiment in order to improve precision. And then, of course, finally, we are also very related to the use of machine learning in IV, including work by Damian Kozbur, who is the discussant today, on using rich regression in the first stage. So what do we do relative to this? So what we're trying to do here is we provide some motivation of why compliance weighting specifically is a relevant way of using covariates in IV. Then we provide an interpretation of the resulting estimand and large sample theory in a potential outcomes framework. And finally, we provide tools for valid inference that remain valid if you use machine learning in the first stage to estimate compliance. So with that, sorry, I just accidentally jumped to my references. Okay, with that, let me now go over the main part of the talk. So just to provide a simple outline here, I will now first start with a simple linear framework in order to motivate compliance weighting, before then going over to a potential outcomes framework where I drop some of the linearity assumption and discuss properties. And I will stop for questions after that first part of motivating everything in a linear model. So in order to motivate the main results that I want to discuss today, let's consider a very simple linear model with a homogeneous treatment effect, where I'm assuming that some outcome is a linear function of treatment, but that the error term is probably potentially correlated with the treatment D, and that I therefore want to use my instrument Z in order to get rid of the endogeneity. And in this context, I have two principal ways in which I could use covariates. So a first way in which I could use covariates would simply be I run my typical two-stage least squares or IV estimator, but I'm including covariates in order to reduce the variance by controlling for them. So effectively by reducing the variation in the error terms in my regression. So that's not what I want to focus on today. That's certainly something we should be doing. And in the extensions, we have some remarks about how to do that nonparametrically in the context of IV. Instead, what I want to focus on today is a second way in which we could use covariates in an IV framework, which instead says, well, if we have covariates available, and here I'm assuming that these covariates are independent of the treatment, so that treatment randomization happens unconditionally. In that case, I could also think about forming new instruments by acknowledging that by interacting my instrument with those covariates, I may obtain new instruments that are still valid in the sense that there is no covariance of the instrument with the error term in my regression. And so therefore, today, what I want to focus on is what is the structure of those instruments, if we want to ensure that they remain valid, but also that they reduce the variance of the resulting IV estimator, and how can we estimate them in practice. So I therefore now focus on the case where the instrument I consider includes interactions, so is a function of both the instrument and the covariates X. I'm also assuming, for simplicity, that the error terms in my regression are homoscedastic, which is a relatively strong and somewhat artificially strong restriction here, but one that I make in order to simplify the exposition until I show you some more general results. So under some standard asymptotics, assuming I use some instrument that is a function of both the instrument and the covariates, and I assume that this function is fixed. So I'm not talking so far at all about learning such a function H. We can just use standard asymptotics to show that the resulting estimator is squared of n consistent and asymptotically normal and has a variance that is related to both the variance of the instrument and the covariance of the instrument with the treatment. And specifically, I can rewrite this variance in terms of the prediction quality of my first stage estimation exercise, where I predict the treatment from this instrument. So specifically, the variance takes a specific form, which is the residual variance sigma squared divided by the variance of the treatment times the R squared in the first stage regression of the treatment on the instrument. And therefore, there's a very tight link here in this admittedly very simplistic example between first stage prediction quality and the variance of the resulting IV estimator, which basically says that the better my R squared is, the better I'm able to estimate treatment from the instrument, the lower the resulting variance. So that basically suggests an optimization problem. It says in order to find a good instrument, we should simply minimize the mean squared error of predicting the treatment from the instrument among all the instruments that remain valid, meaning among all instruments that are not correlated with the second stage error term. And so in order to solve this problem, which is maximize the fit in the first stage subject to the instrument being valid, I now focus first on this second condition, which is subject to the instrument being valid. So I'm now asking myself, how can I ensure that the instrument is valid before optimizing for optimal fit? So first of all, I want to note that there is one natural candidate for the case of a binary instrument, which is the case that I focus on today, which is I could simply recenter the instrument by the probability P of the instrument being 1. And I could then multiply that by some function, which I write as a W of X here, of the covariates X. So assume I do that, then we can plug this into the covariance between the error term and the instrument. And because I assume that the instrument is both independent of the error term and of the covariates X, do I know that the resulting instrument will also be valid in the sense that there will be no correlation with the error term in the first stage? Now, this admittedly is one very specific and one simple instrument, but our main first result is basically that any instrument that is valid by construction, meaning any instrument for which the correlation between the error term and the instrument is 0, for any distribution where the X and the epsilon is independent of the instrument, takes that form. So up to an added constant and a multiplicative scaling, basically, any instrument that is valid in this context with binary instrument Z can be written in this form. And so based on this first result, I can now switch my interest in optimizing over rather than an instrument with interactions H of Z and X, instead optimizing over instruments that take the specific form of a weighting function W of X multiplied by the recentered instrument Z minus P. And I can then ask among those instruments, specifically among those weighting functions, what is the optimal weighting function that maximizes the fit, meaning minimizes the mean squared error in predicting D, when I choose only weighting functions. And the answer of that is that in our simple homoscedastic and homogeneous reference case that I started this section with, the optimal instrument among this class of instruments is the one that multiplies the recentered instrument exactly by the probability of compliance, which is the probability of being treated or the conditional expectation of treatment given being assigned to treatment and the covariate X, minus the conditional expectation of treatment given that you are not assigned to treatment and the covariate X. And so in that way, the prediction problem in the first stage is solved exactly by the recentered instrument multiplied by compliance. And this already gives us a connection between the variance minimizing instrument among this class of instruments and compliance. And I now want to shed some more light on how to interpret this instrument and connect it to some of the existing literature. So specifically, so far I've assumed that I'm forming an IV estimator by using W of X times Z minus P, so my weighted instrument, as an instrument. So effectively, the way that I would do that is I would form an estimate by using the empirical covariance between my outcome Y and this instrument, and normalize it by the empirical covariance of the endogenous treatment D and that constructed instrument. I could alternatively interpret what I'm doing here as running an IV regression where I take the empirical covariance of the outcome and the instrument normalized by the empirical covariance of the treatment and the instrument, but I include a weight in that regression. Now, it turns out that those two are not mechanically exactly the same because the two covariances are normalized in slightly different ways. However, as long as we include the weight itself as a control in our IV regression, then those two are exactly equivalent. And from now on, I will basically equivalently talk about an instrument that includes the weight and simply running a weighted IV regression. So specifically, this connects what I have done in terms of motivation so far neatly to compliance-weighted instrumental variables and the papers I mentioned earlier, and also to Nick Huntington-Klein's work, who considers both grouping by compliance as well as weighting by compliance. And so the next question is now going to be, if I'm dropping the assumptions that I've made so far, which is that I have a linear model with homogeneous treatment effects and homoscedastic error terms, and I'm instead assuming all this in a general potential outcomes framework, what are the properties of this weighted estimator, and how should we choose the weight optimal in general? And then how can we do inference on those estimates? Before that, let me pause there and see whether any questions that would make sense to answer publicly.
So at the moment, we don't have open questions, but I would encourage the audience to submit questions, please. So yeah, I think for now, please continue with your talk, Jann.
Okay, thank you. So I now want to consider this estimator that I just motivated in a potential outcomes framework. And to be clear what we're doing here, we're now assuming that we have a simple binary instrument Z. We have simple endogenous binary treatment D. So that would be the equivalent of encouraging people to take up a medication, and D would be whether people to actually take up medication. I have some outcome of interest Y, which could be a health outcome, but I know that there is selection into treatment. So simply taking the effect of treatment D on Y would not work. So instead I'm running an IV regression, but I've now added one crucial part, which is I've added a weight to that regression. And I'm assuming that I'm running all this weighting by some functions of X, which for now I'm taking as fixed. And later I will talk about estimating. I'm doing all this in a potential outcomes framework. So I'm assuming that I write D of 1 for those people, for the treatment status of those people who are assigned to treatment, so who have Z equals to 1, and D of 0 for the potential outcome of those people, for the potential treatment, sorry, of those people that are assigned to control. And so as I mentioned before, in that framework, there are now 4 different types of people in my sample. There are those people that react to the treatment, so that take the treatment up if and only if they're assigned to treatment, always takers who always take the treatment, never takers who never take the treatment, and finally fires. And in order to be able to identify causal effects in this framework, I'm now making the standard assumptions in the late framework for identification, which is I'm going to assume that there are no defiers. And then I'm going to also assume exclusion, meaning the instrument only affects the outcome through the treatment, that the treatment itself is randomly assigned, which here includes randomly assigned relative to the covariates X, and that the treatment is, that the instrument is relevant, meaning that it actually creates a positive probability of compliance. Under these assumptions, we know well that what is identified is the local average treatment effect, meaning the causal effect of the treatment on compliers. We can say a little bit more once we include covariates X. Specifically in this case, not only the overall average, local average treatment effect is identified, but the local average treatment effect is also identified conditional on the covariates X. So here I'm now going to route tau of X for the conditional lates. So what does our weighted estimator do if we analyze it in this framework? Well, under standard regularity conditions for the convergence of the IV estimator, the weighted IV estimator is consistent for a weighted late, where that weighted late we can think of as the average treatment effect among compliers weighted by the weights that we included. So there's no surprise there, which I can equivalently write as the expectation of the weight multiplied by compliance multiplied by the treatment effect, where I'm writing alpha of X for compliance, meaning for the probability of reacting to treatment, which here means that you are in taking up treatment if and only if you are assigned to the treatment group. So what are some specific cases of this weighted late? The first one would be if we simply consider constant weighting. So we're not doing any weighting, we're just running the standard late. In this case, the standard result in this literature is that the estimand of the IV estimator is a local average treatment effect, which is exactly the weighted conditional late where the weighting happens by compliance. If instead we now use compliance itself as a weight, which is what I suggested in the linear model before as being the choice that minimizes the asymptotic variance, then we obtain what Huntington-Klein calls a superlate, which effectively adds an additional weighting by compliance. So rather than only weighting by compliance by conditioning on d of 1 being greater than d of 0, we now add an additional weight, which effectively means that we're doubling down on compliance weighting and weighting the conditional lates by treatment effect squared. Now, you can think of different ways of weighting the conditional lates here. For example, you could also think of specifically using X covariates that you think are actually not correlated with variation in treatment effects. So in this case, weighting would not actually change your estimand because that weighting may be orthogonal to any variation you have in your conditional lates. However, whatever you do, I just want to point out that the resulting treatment effects will still be weights over conditional lates. So there's no way of getting around the fact that we still can only estimate treatment effects on the compliers, even if you do so conditional on X. Now that I've shown you the estimand, meaning the parameter that these weighted lates converge to, I now want to discuss as the asymptotic distribution of the weighted late, again for a fixed weight. So specifically, we can do the standard IV theory here and simply show that the weighted late relative to its weighted estimand converges to a large sample normal distribution, where the variance depends on the weights as well of the variance of the residual and the compliance. And so why is this interesting? Well, we can now look at this asymptotic variance, and we can use Cauchy-Schwarz to talk about which rating W would make this variance as small as possible. And the answer is that the optimal variance that we should choose here in this general case, we have not made any assumptions about the homogeneity of treatment effects or the homoscedasticity of regression residuals, is basically the compliance normalized by the variance of the residuals. So in other words, if you had information about compliance and you had information about the variance of residuals, the optimal way of achieving minimal variance here would be to choose a weight that trades off compliance on the one hand side with variance on the other. And we can then also say what the resulting optimal variance is, and I have the expression on the slide here. So one thing I want to point out here, however, is that by choosing different weights, we are not just choosing the asymptotic variance, we are also affecting the estimand itself. So one additional thing that we do in the paper, which I'm not showing here, is that we are also characterizing under which conditions we do better, not just relative to this estimand as itself a weighted late, but instead cases in which we do better according to the original late. So if you were really interested in estimating the average treatment effect among compliers, then we change the estimand, but we argue that as long as the treatment effect heterogeneity is small, then the difference between that estimand that weights in the estimand relative to the standard late is not that large, and you may still be able to do better even relative to the estimand you may have originally cared about. Let me just check again whether there are any questions at this point that would be worth answering appropriately.
So we, again, don't have open questions. Stephen did answer one question in the Q&A. So you may continue. I do have, could I ask a clarifying question?
Oh, yeah, absolutely, please.
All right. Do you mind going back to slides 9 or 10? Sorry for making you go back so much.
Not at all.
All right.
Check.
Okay, great. So could you actually go back to the previous slides?
Mm-hmm.
I just have a question about this X and Z and the function HZX. So here, just looking at this graph, I would assume that you have the assumption that X is independent of epsilon. That is not exactly what you're assuming though, right? You're assuming that this homoscedasticity with respect to epsilon and X, and later you will assume, yeah, this covariance of epsilon and this function of Z and X is 0. So that seems to be enough.
That's a great point. So I think you're right in that here, I am not assuming that X is unrelated to the epsilon. So specifically, I'm not assuming that X is necessarily an instrument. I'm only assuming that it's an instrument so that I can say something about how I can construct instruments from that remain valid.
And this function H of Z and X, that's does it have a particular form? Is it some linear function or something?
Yeah, so I'm starting here with any general function that I can have, but then I'm arguing that if I want to ensure this covariance condition on the right here, then I have to choose it in a specific form. And the way that I can actually characterize that is by basically not making any restrictions on the distribution of epsilon and X, but simultaneously assuming that Z is binary, and that makes it tractable. So that combination of a very simple structure in Z, while being unrestricted in epsilon and X, allows me to basically say that if I want to ensure that for whatever the distribution of X and epsilon is, as long as I know that it's independent of Z, I have this orthogonality, meaning my instrument is valid, then I can tell you that it must take, in general, this form of multiplying a weight by the normalized instrument, because with any other combination, I could effectively construct some structure of the error term and of the X that would create some endogeneity problem if I use that as an instrument.
I see. All right, thank you, Jann.
Okay, great. So let me continue and now go into empirical implementation. So what I have done so far is I have assumed that my weight is fixed and given, but now I want to consider what happens if I actually estimate that from beta. Specifically, I want to focus on the case where our goal is to weight by compliance. I argued before that we may also want to weight by variance, which is an interesting extension that would be covered by the asymptotic theory we provide here. But for now, in the simulations, we're considering simply weighting by compliance. So the first thing I want to point out is that compliance is effectively a conditional average treatment effect. So it is the effect that the instrument has on the endogenous treatment conditional on X. So I can write it as the difference between two conditional expectations in the assigned and in the non-assigned group. And this motivates can use machine learning tools from causal machine learning, specifically those that are built in order to estimate causal effects, in order to estimate that weight. And here we do also what Huntington-Klein does, which is we use the causal forest in order to estimate heterogeneous effects, which in this case is a causal forest applied to the first stage problem of the effect of the instrument on treatment. And then we use the standard machine learning playbook with crossfitting, meaning we perform a k-fold crossfitting, where we always estimate compliance on k-1 of the folds, and then extrapolate our compliance predictions to the left out fold. We construct weights from those compliance predictions on the held out folds and then run a weighted two-stage least squares estimator in order to obtain an estimator that now uses those estimated weights. And we're now interested in deriving the asymptotic distribution of that weighted estimator, where here I actually want to be agnostic about the weight W hat and how it is constructed as much as I can. Specifically, I don't want to base what we're doing now on whether we're actually able to estimate compliance well or not. But instead, I want to simply assume that we have some estimate W hat that is estimated in this cross-fitting framework. And I want to ask what we can say about the asymptotic distribution. So I specifically now consider the IV estimator that uses the empirical weights. And I want to ask how the large sample distribution behaves relative to the weighted late, which puts this additional weight into the typical expression for the local average treatment effect. And so our first result is if those weights are indeed fitted with k-fold cross-fitting and they converge to some function W, where I only need consistency in an L2 sense, so I don't need any specific rate, then the estimator on the left is consistent for the estimate on the right, in the sense that we converge in probability to the W-weighted late. Now that, of course, only tells me something about consistency. In practice, I may also want to do inference, and I may want to construct standard errors and learn something about the distribution around that estimate. And here, there is a challenge, which is that the estimate itself depends on the weight, which I'm estimating possibly non-parametrically and possibly at slower than the parametric rate. And therefore, without imposing some structure on the estimand or its estimation or the conditional treatment effects, in general, there is no hope to achieve square root of n consistency and asymptotic normality of this estimator. And let me make precise why this is the case. So take a very simple case where the X covariate only takes a finite number of values. So in this case, I could construct a DGP where the treatment effect is effectively the indicator of having a certain value of X. So that means the treatment effect is 1 for one specific value of X and 0 otherwise. So that would make the estimate that I'm estimating here equal to the value of the weight at one specific value. So in this case, if we were able to make inference, if we were able to establish square root of n consistency and asymptotic normality in general for our estimator, no matter which assumptions we put on the weight function, then we would actually also have to be able to get square root of n consistent estimation for values of the weight function itself, which we don't want to assume here. So this is just saying that there may be ways of doing better in the sense that we may be able to achieve square root of n consistency and asymptotic normality if we impose some additional structure. But with the little structure we imposed here, there's no hope in general to achieve that. And we are therefore going a slightly different route.
Jann, sorry to interrupt you. Just wanted to remind you of the time. You have around 5 minutes left.
Thank you, perfect. So our solution to the problem that in general, we don't have much hope here to achieve square root of n consistency relative to the weighted late, because that weighted late itself includes the weight, is to instead use an estimand that it is itself depending on the weights that I estimate in the sample. So think of it as the following way. Rather than making the estimand whatever the population weights would be, we instead make the estimand a weighted average of conditional lates, where those weights are whatever the weights are I estimate in my sample. And specifically, the way we do that is we use the weighting functions that we get in our cross-fitting estimation, and then we take the average over all those folds, which means effectively that we weight our lates, our conditional lates, by an average of the k weight functions that we obtain in our sample, and we condition on those weight functions themselves. And so relative to this empirical estimand, we can still achieve the standard square root of n consistency and asymptotic normality with a variance that is the same as the variance that we would have achieved had we known the weight. And so that basically mimics the conditional inference approach in Viktor Chernozukov and co-authors' work on estimating heterogeneous treatment effects, where they also distinguish basically between variation that comes from constructing certain machine learning nuisance components in the data from the remaining variation. We can also, in the same set of assumptions, provide robust standard errors in the weighted regression and estimate this asymptotic variance consistently. And then finally, if you're actually interested in getting square root of n consistency relative to the population estimand, we can also provide that, providing that the variation in treatment effects is of second order. So if the variance is of order 1 over n, which for example would happen if your treatment effects overall are very small, which may be the reason why you care a lot about variance because they are local to 0, then we would still get the standard asymptotic normality. Okay, since I only have a few minutes left, I will finish the talk and then we can take some questions after if we have time. So I now simply want to show some simulation results. You can read up on the details of our simulation study in the paper. The idea is that we provide a DGP that allows us to correlate the treatment effects with compliance, as well as provide heteroscedastic and homoscedastic cases, where in all of those cases, what we're doing is we're comparing different ways of estimating compliance weights and looking at their performance. So let me just give you some pictures to give you a flavor of what we find here. So in this case, this is the case of homogeneous treatment effects and homoscedastic error terms. In a way, it's the best case scenario. We are varying from top to bottom the ability of the X covariates to predict compliance. And so you can see if our ability to predict compliance is very good on top, then an estimator that weights by compliance which is the black estimator in this case, is more tightly centered around our estimand, which in this case we assume is the population local average treatment effect, while the standard IV estimator is more spread out and the OLS estimator is much more concentrated, but estimates the wrong estimand because of endogeneity. And so the gap here between the compliance-weighted IV and IV, of course, goes down as our ability to predict well using the covariates goes down. We then implement this in different ways. Specifically here, I'm showing you an implementation that uses cross-fitting as we do in our theory and uses either OLS in order to predict the compliance or uses the honest causal forest to do so. And we see that especially when we have a relatively strong relationship between the covariates and compliance, which is the top row, the honest causal forest can reduce in our simulation the variance or the root mean squared error in this case of the two-stage square estimators by out of magnitude 25%, which almost achieves the 30% in the left column that we can achieve using optimal weights. And depending on how homogeneous treatment effects are and how heteroscedastic the error terms are, this performance will be slightly better or worse. Specifically with heterogeneous treatment effects, our performance in root mean squared error relative to the population late will get slightly worse because we're also changing the estimand, which adds some loss. While heteroscedasticity, in this case, if we don't weight by an estimation of the variance, can either improve or make our performance worse, depending on the correlation of heteroscedasticity with our weights. So if heteroscedasticity is positively correlated, it makes the performance worse. If it is negatively correlated with compliance, then it even makes performance even better relative to the two-stage squares estimator, because we now effectively also happen to weight those units more that have a lower residual variance. I now want to finish by discussing a few extensions. So first of all, I already mentioned that the optimal weight in principle does not only include compliance, but also variance. And so one interesting extension here is also including variance, which we so far have implemented using existing tools and literature, specifically a proposal by Miller and Starks. Second, you also want to use control variables to residualize in order to reduce residual variation, which we can also do non-parametrically using existing proposals in the literature. And finally, we also tried out what happens if we actually don't use cross-fitting, but instead we use in-sample or on-it estimation without cross-fitting, which is also something that Huntington-Klein considers in his paper. And one interesting result here is that actually by doing honest estimation that does not use cross-fitting, when the ability to predict compliance is relatively high, it doesn't make a big difference. But as the ability to predict compliance goes bad, it actually looks like using in-sample predictions here that do not do cross-fitting may do even better than what we're already doing. However, our current theory doesn't apply to that. So I think one interesting extension here would be to take our theory and think about what we can still say about the case where we don't rely on strict cross-fitting. So let me now summarize and conclude. So the starting point of my talk today was that IV regression usually reduces bias, but it's often very noisy. With high-dimensional instruments in the first stage, we could improve that by using machine learning to solve the implicit prediction problem that is behind IV. But in many cases, the instruments we use may actually be very simple. For example, may only be binary. And I asked today whether we still can use machine learning tools for high-dimensional prediction in order to prove inference in this case. And I started by characterizing valid instruments that we obtained from covariate interactions, then related those to efficient weighting by compliance in a late framework where I did not make any assumptions about linearity, homogeneity, or homoscedasticity, and then discussed a specific implementation with sample splitting and discussed the large sample distribution of the estimator that we consider here in that framework. So taken together, for me, one takeaway here is that machine learning has powerful applications in the first stage of IV because there's an implicit prediction problem here. With simple instruments, however, the problem that we want to solve using machine learning is really a causal problem of estimating a conditional average treatment effect and not a simple prediction problem. And inference becomes non-trivial because the estimand that we consider here is itself driven by the data. And with that, thanks a lot. And thanks, Damian, for discussing.
Thanks for the very nice talk. I think we have a question that Emma.
Yes. Thank you, Jann. So we have a question that was flagged by Stephen. So the question says, what happens if X is related to Z? For example, if X is a cause of Z, is there still a way to apply this method?
Yes, I think that's a great question. So first of all, the characterization of instruments that remain valid here would go through if you recenter by a propensity score that depends on X. So let me quickly go back to the picture of the instruments that I showed here, where I argued that the form of the instruments is generally the weight times Z minus P. You could still extend everything we do here by including a dependence of this propensity score for the instrument on X. But let me say two things about that. First of all, our current theory depends on you knowing the propensity score. So I would say if you knew the propensity score on you in this case, then you are still fine to apply everything as I show it here. However, if you also have to estimate it, you run into questions of double robustness, and you will want to estimate the propensity score in a way that ensures that you still get inference. Second thing I should say is I think that really Kirill Borusyak and Peter Hull's paper with the paper to look for that, because they specifically consider the case where there is a challenge because the instrument is actually not unconditionally valid, and argue that you should do exactly that recentering, basically arriving at a very similar result. So I don't think we have anything specifically to say about that. And I think their paper is the more natural place for that. But there are definitely connections there.
Great, thank you. Then I think it's time to switch over to the discussion. So Damian and Kozbur will do the discussion. After that, Jann, you will have the opportunity to respond.
Thank you very much. Can somebody share this slide? Or is that necessary? Well, okay, let me begin. Thank you to the organizing committee for the invitation to be a discussant, and thank you to Jann and Stephen for contributing a thought-provoking paper. When the final goal of a research study is inference for a treatment effect, incorporating machine learning, otherwise called ML techniques, into estimation is not for the faint of heart. One reason for this is that so many subtle, unexpected things can go wrong. Careful research needs to account for all of them to reach credible conclusions. Today's paper is concerned with improving instrumental variables, or IV estimation, by using ML techniques to calculate improved estimates of compliance probabilities. IV is an incredibly commonly used set of methods for calculating treatment effects in the absence of randomization of treatment. However, available exogenous instruments are often only weakly correlated with treatment status, which is well known to lead to imprecision of final treatment effect estimates. If policymakers use estimates to inform policy, then precision is important to ensure intended effects upon enactment. Academic economists with basic research questions also benefit from precise estimation, and ML techniques present an opportunity for improving precision. Today's paper assumes that the instrument Z is fully independent of covariates X and treatment status D. That assumption is approximately equivalent to assuming the data comes from a randomized trial which randomly assigns values of Z to observational units. As a result, one might sensibly revert to classical IV techniques over ML techniques to estimate treatment effects because they are known to work under widely understood regularity conditions. Moreover, in the event of a randomized trial, the researchers have some scope to engineer an instrument which is more likely to strongly influence treatment status. So, is it worth it to leave the safe waters of classical estimation to play with the fire that is machine learning in this context? The answer to this question depends on several things, including an assessment of what could go wrong, the objectives of the researchers, or the availability of prior knowledge about which ML techniques are likely to work in the given application. Let me first give an illustration about what could go wrong. A high-level assumption maintained in the current paper is that compliance probabilities are a consistently estimated function of X and Z within each iteration of a cross-validation loop. Consistency is, foremost, a qualitative property which states that the likely magnitude of estimation error of a given method is suitably small. But even under rigorous formalism, there's a fine line between consistency and inconsistency. Suppose that compliance probabilities are estimated under the commonly used high-dimensional linear regression specification, in which the number of regressors is larger than the sample size. Consider two related techniques, ridge regression and lasso regression. With ridge, estimated compliance probabilities cannot generally be consistent. With lasso, estimated compliance probabilities are consistent under a further sparsity assumption. It stands to reason that under moderate departures from sparsity, bounds encoded in the definition of consistency of lasso will be moderately violated. In such situations, it is unclear whether the formally consistent lasso or the formally inconsistent ridge performs better in a given data set. Now reconsider the assumption from today's paper that compliance probabilities are consistently estimated within cross-validation iterations, and think about blurring the line between consistency and inconsistency. As the number of cross-validation iterations increases, for example, going from 10-fold to n-fold, or leave one out cross-validation, and consistency becomes moderately violated, a new term appears in the asymptotic variance of the final treatment effects estimate. This new term is a use statistic, which also arises in standard many instrument asymptotics analysis for jackknife head beam. Ignoring this term can lead to reporting confidence intervals which are too narrow. So, practical pitfalls are lurking potentially everywhere. But on a more hopeful note, pitfalls can be avoided if they can be cataloged and understood. With that, let me continue discussing potential benefits of ML, which I touched on earlier. For industry applications, acting upon even small treatment effects can lead to large benefits in terms of revenue, for example, if accumulated over a large potential customer base. Detecting small effects requires precise measurement. Also, like before, for basic academic research, precise estimates just may lead to new important discoveries. Today's paper proceeds to contribute new methods in the hopes of reducing the risks and increasing the benefits associated with using ML for treatment effects. An interesting contribution of this paper is it characterizes the types of functions of X and Z which are allowable for approximating compliance probabilities. Estimating compliance probabilities with general ML techniques, but staying within this class of functions, leads to final treatment effect estimates which are not contaminated by the use of ML. Therefore, Jann and Stephen's contribution adds to a line of methodological research on shielding treatment effects estimates from any possible complications arising from incorporating ML techniques. For an early example of this literature, which Jann even mentioned, split sample IB solves the problem that ex-ante exogenous instruments are no longer conditionally exogenous if conditioned on having undergone formal model selection in a first stage regression. And there are also practical challenges that lie ahead, to name just one of many, which remains relevant even in the context of randomized assignment of Z, which is how to implement approximations which help speed up computation in a way that preserves estimates of treatment effects. To conclude, this paper continues the trek towards a robust and comprehensive understanding of the behavior of ML techniques in the context of treatment effect estimation. Marching onwards in this manner is ultimately the right path to mastering the fire that is machine learning, to avoiding being burned by its risks, and to harnessing its benefits. Thank you.
All right, thanks for the nice discussion. Jann, do you want to respond?
I really appreciate the discussion, and I love the metaphors you used as well. I agree with the one big challenge here, which is how should we capture machine learning as something that aims to estimate something, but we often may not have consistency guarantees for? Can we somehow harness the fact that, empirically machine learning does better in one problem than another, and therefore can we rely on simply the one that has better empirical performance? How can we translate that into those consistency statements? And I think it's a bit of an interesting open question in generalist literature. What the right high-level conditions are we willing to assume for machine learning? And so I think it was a good reminder of that tension and good food for thought. So thanks a lot.
All right, great. I think we are running out of time, so I'll just quickly wrap up and then we can continue discussion or if there are any further questions. So first of all, thank you so much, Jann, for a very nice talk, and Damian for a nice discussion. Also, thank you to Stephen for helping out in Q&A. Next week, we're going to have Roshan Xiong from Emory University. I hope I pronounced it correctly, probably not, who will talk about efficient treatment effect estimation observational studies on the heterogeneous partial interference. Thank you all for coming today. I hope you have a great week and see you next time.